All right, thank you guys. With that, I'll kind of just jump straight into my presentation here. As we've seen already discussed in the earlier session this morning, and within this session, particularly the last two talks acting as good intros to what I'm going to talk about today, there's been a real increased focus on fugitive emissions from oil and gas wells within the past 3 or 4 years. Specifically, there's been a big focus on quantifying fugitive methane leakage from natural gas wells, mainly due to the large role that natural gas will likely play in any future energy system within the United States. Despite such a focus, however, such leakage rates are still fairly poorly understood. Most of this is due to a lack of on-the-ground, bottom-up studies that have been completed. There are a number of studies that have recently come out in the past week from EDF with Dave Allen that have done a good job at looking at this, and there are some previous ones. However, by and large, these studies are expensive and very time-consuming, and as such, there have not been too many of them. There is one study that has existed for the Fort Worth area. It was completed in 2011, that looked at a region, the Barnett, with hundreds of wells that used well stimulation. These results are freely available online. So what we wanted to do was take this data, and change the main focus to look at really how this would apply to fugitive methane emissions, and see what more could we really learn from this data set. So going into this, we wanted to do 3 main things. We wanted to first improve the granularity of the data set to see how it could apply to what we're interested in. We wanted to look at some leakage rates on a per well and per component basis. And we also wanted to develop emission factors and see how we could compare those with the published literature. So talking a little bit about the study was commissioned by the City of Fort Worth and prepared by Eastern Research Group and Sage Environmental in 2011, with the main goal of looking and quantifying air quality impacts of local natural gas production exploration activity. So they tackled this with trying to address 4 main questions. First, they wanted to see how much air pollution was being released by these sites, then whether these sites were in regulatory compliance with local and state environmental regulation. They wanted to look at what the impacts on off-site air pollution levels were, and then lastly, the impacts on public health. The study was split up into 6 main sections. The section relevant to our work was that of point source testing. The study went on and measured a large number of sites. They measured 375 well pads that accounted for over 1,000 wells. They also measured a number of other different sites, such as compressor stations, processing facilities, and drilling and fracking operations. However, we felt that the number of sites measured in those cases was not large enough of a sample size for us to use, so our focus of our work was on the well pads and wells. The total number of connectors was extremely large, of components was extremely large, with them accounting for nearly 650,000 connectors. These were not all necessarily connectors that were measured, valves that were measured. These are just accounted for. So they measured a portion of these emissions on a point source base and extrapolated much of the results to the rest. So to briefly touch on the measurement procedure, they first would use an infrared camera around the site that would allow them to pick up large concentration emissions. So we're looking at emissions with concentrations greater than 10,000 parts per million by volume. They would measure and record these leaks. Then a toxic vapor analyzer was used on approximately 10% of all components. This accounts for the smaller leaks that were not detected by an IR camera. Since only 10% of these components were measured, it was extrapolated through the rest of the components. Lastly, a high flow sampler, which will measure flow rate. So specifically in this work, we're looking at the leakage rate that we're trying to measure, was used on all of these points. And additionally, they collected 164 canisters, which is really impressive, in order to speciate emissions. So this allowed them for each leak to find out the exact emission rates of HAPs, non-VOCs, and VOCs additionally. So this is just a screenshot straight from the spreadsheet that we're using. For each leak, they had detailed information on component and leak type, as well as location, and as, like I mentioned, the emission speciation. So in the red, right here, the red section you see is the 3 broad course categories that they decided upon. So they decided on classifying them as valves, connectors, and other, which is a very broad categorization. However, originally when they recorded the information, they also included, on the leftmost column, dozens of specific categories. There's actually 94 unique leak types that they included, which is a large number. And then on the right is even more detailed information. So for components that were labeled as other, they give more specific information. What we wanted to do was really come up with kind of an intermediate classification. We felt that 3 categories was too coarse, with over 60% of the leaks being classified as other, and we felt that the 94 categories in the leftmost column was just too many. So we came up first with our own categorization, then we talked with a number of industry experts from different groups, heard what they had to say, and adjusted our categories. So we asked them questions like what can necessarily be classified as a pneumatic device, as well as more specific questions like what exactly is the difference between a Murphy pressure indicator and a regular pressure indicator. Through their help, we were able to develop 8 total emission categories. It's important to note that the emission categories that we decided upon are not necessarily a silver bullet. Rather, this is just our best interpretation. There's plenty of different ways that you can go about categorizing these leaks, and different people we talked to had different suggestions as well. So here is just looking at methane leakage as split up by the different leak types. On the left is the old course classification. On the right is the new classification. On the left you see the largest area is other, which doesn't really tell us too much. However, on the right we were able to definitely split that up. The other section is now very small, and we see that the largest component contributions to methane leakage comes from pneumatics and tanks. On the recommendation of some of these people we talked to, they recommended we try and split up tanks into condensate and water tanks. As in the data set, most of them were unclassified. We had information on about 20 tank leaks as to whether it was a condensate or water tank. And we saw that we hoped to look at the VOC and ethane ratio versus methane. Normally you'd expect water tanks to have a higher ratio of VOC and ethane. Unfortunately, we were unable to really see anything that would allow us to further split up this tank category. There's a large linear trend through in the middle of the graph. This is due to one canister being applied to multiple different leaks, so the same ratio would apply. Here's just one distribution that we looked at. This is looking at methane on a per well basis. So the first thing to notice is that it's a heavy tail distribution, and this is something that we've gotten to see in other work recently now, with a small number of wells contributing greatly to total methane emissions. You can see the mean is around the 75th percentile, so you have these few wells bringing this up. We also looked at distributions on a per component basis that I haven't included here, but you also see a similar heavy tail distribution for all components. So it's the same thing. It's not just wells that are contributing greatly, it's also components that are contributing greatly or the most to methane emissions for well pads. We were able to develop emission factors for valves, connectors, tanks, and compressors. We see on this large graph here that we compared with previously published numbers. So on the left, we have markers for different published literature from 95 to more recent results from California Air Resources Board. There's a large distribution, a large range within that of the published literature, and our numbers tend to come in around the middle of the distribution for both valves and connectors. One thing that's of interest to see is the California Air Resources Board numbers, which are both very low for valves and connectors. This could be down to a number of different things. First off, this could be representative of California with stricter regulations here in California than other states in the country. Or additionally, I believe the California Air Resources Board was a self-reported survey. So these numbers could be, some of the numbers could have been misrepresented by those submitting the numbers. We had hoped to be able to compare our numbers for tanks with emission factors that were previously published from the EPA greenhouse gas inventory, but as I mentioned, we were unable to split them up into water and condensate tanks, which made it difficult for comparisons. Additionally, many numbers for tanks through the inventory were given in terms of barrel throughput, not kilograms per year as numbers we had. Unfortunately, we were unable to develop an emission factor for pneumatic devices, despite looking greatly at that. This is because we didn't have any idea as to how many total pneumatic devices were located on these sites. They measured how many total valves, connectors, tanks, and compressors there were, but they neglected to measure total number of pneumatics. So we were unable to compare with some of Dave Allen's work on extensive work on pneumatic devices. So kind of in conclusion here, one of the things that we've seen is that most of these distributions on a component and well basis are heavy-tailed. So specifically to this work, we saw that around 0.3% of all components contributed to 99.4% of total methane emissions. This is a good thing to hear, as this means that if we can properly detect and repair these leaks, then this issue of fugitive methane emissions can be a much smaller issue. But it's a matter first of being able to detect these emissions in the first place. We also, another key takeaway is that we were unable to really align inventories and emission factors together. We were able to compare some numbers, but by and large, there's just a lot of variability when you look at different inventories, which is a real shame. So that kind of leads me to my 2 recommendations and takeaways from this work. First off, we need more studies of this scope. We need more bottom-up, on-the-ground studies that allow us to really quantify and fully understand this issue of methane leakage. And secondly, these studies aren't going to be useful unless we have a standardized classification scheme that allows for easy comparisons between different inventories and different studies. This is really key moving forward and it's definitely my highest recommendation from this work. Looking forward, one thing we're looking at doing is getting a total system methane leakage rate. So this would look at how much total methane we have leaking from our measured leakage sites and comparing that to total throughput numbers we can get through the Railroad Commission of Texas. And then also we would like to compare with the recent EDF results that came out about a week ago. Lastly, I'd just like to thank Richard Neville and the Stanford School of Earth Sciences undergraduate research program for providing funding and support for this work. I'd like to thank the Stanford Department of Energy Resources Engineering, as well as the California Council on Science and Technology. Thank you.
Well, we have a few minutes for questions. Questions? I actually have a question. Did you look it up, the emissions from the flowback of the situation
From flowback?
flowbacks?
That's a good question. We weren't really able to look at that too much. We didn't have necessarily the data to look at that in this extensive. We only really had fugitive emissions, so like per component basis. Yeah.